All right. I hope I am audible. Checking recordings first.
Yes.
Thank you, Richard. All right. So let's get started for today's class. So today, what we are going to do is we are going to solve two problems in combustion. Uh, and before I go ahead and solve the problems, I would like to know if you have any questions from your side, Richard.
Sir, I want to know that during exam, for the exams, sir, the problems you are discussing are enough and the assignment questions, or we have to study some practice problem from other books?
Probably what I feel is whatever I solve is and whatever is given in the assignments
Yes, sir.
basically should be enough for your exams, I feel. But it is always better to solve extra problems so that you will.
Yes, sir.
So it's better to solve extra problems, let's say from Yunus Essential book, Senjal and Simbala book, or you can also take a Shapiro book, right? So these two are
Okay, sir.
recommended books for the course. So you can
Yes, sir.
open it and solve some of the problems there also. It is better to have a good uh, for an exam. So that's just what.
Okay, sir. Thank you, sir.
All right. So if you don't have any questions, let me solve today's problems. Today's problem is going
Yes,
to
sir.
involve combustion, and yes, I have one question which is simpler, and the second question involves a combustion happening inside a rocket motor, the liquid propellant rocket motor. We will solve it by hand, and also I will show you a demo about how it can be solved using uh, you know open source software. So here I am going to use NASA CEA. Um, so we will see how NASA CEA can be used to calculate whatever we try to do it by hand. Okay. Uh,
Yes, sir.
all right. So So this question, so both of the questions are basically, this question is actually taken from Senjal only, and the other question is actually taken from one of the rocket propulsion course from NPTEL only. So I just want to, give something related to uh, so because combustion happens inside rockets, that's what. Anyway, so the first question is going to deal with methyl alcohol percent excess air. So methyl alcohol is burned with air, but with a excess of 100%. And during the combustion process, 60% of the carbon in the fuel is converted to CO2, and 40% is converted to CO. Write the balanced equation, reaction equation, and determine the air fuel ratio. That is what is. Here is a schematic. So we have a combustion chamber here, and there is a methyl alcohol CH3OH is going in, and air is going in, but we have 100% excess air. So whatever is required in addition to it, excess air we have, and the are these products CO2, CO, and you know that ideal product for a combustion is going to be H2O and CO2, right? And CO2, H2O, CO, and since air is excess, we are oxygen and N2, so the excess air has to be there in the product side also, right? So that's why we have O2 and N2 in excess. So these are the combustion products we are considering right now. Ideally, in a combustion chamber, if this is the case, usually what happens, these are not only the products. We will discuss about this later, but for this problem, we will assume that these are the only products coming out, and these are the reactants entering it. So if that is the problem statement, we need to write a balance. Uh, What do you think? How it can be written? We write it down. So only uh, these are the react products H2O. The only products. The assumption basically. We need to write a balanced reaction equation. So this side is going to be reactants, right? CH3OH plus and air. So air, basically it is nothing but O2 plus 3.76 N2. Basically, air contains we can 21% is oxygen and 79% is nitrogen. And so if you all these are by volume or by moles. So if you convert it uh, based on that, let's say nitrogen is 75, right? So 0.779, so 0.79 by 0.21 will basically give you 3.76. That is why we always write air as this 76 N2. Now this is going to give certain products which we already know. It's going to be CO2, CO, and H2O plus. Now, how do we balance this equation? So we said 100% excess, but we don't know it's the right amount. And once only when we know right amount, we can find the excess amount, right? So let's say if I consider this as X, okay, and these are A, B, C, D, and E. So these are the unknowns. So basically, if you find uh, these coefficients, uh, will be done with the balanced region. So how do we find this coefficients? Any idea? So you are thinking too much. Simple. We what we usually do is atom balance, right? But the problem is if we do atom balance, basically we can do atom balance. Like how many atoms we have? We have carbon, we have hydrogen, we have oxygen, and we have nitrogen. So four atoms we have, right? The products we have one, two, three, four, and five products, right? So if we have four atoms, only you can equate it. In fact, six unknowns. So if you look at it, we have, which means you can write four balance equation, atom balance equation, E, H, O, and N, right? But how many unknowns we have? And this is A, right? B, C, D, E. In addition, we also don't know what is X.
6.
Six. Okay. So we have six unknowns, which is nothing but X, A, B, C, D, and E. So now we can write only four atom balance equation, but we cannot find six unknowns. So only four unknowns we can find, but we need two extra equations, right? Uh, so how do we do it? So if you look carefully in the question, so you have during the combustion process, 60% of the carbon in the fuel is converted to CO2 and 40% is converted to CO. So this is the clue. Uh, Based on that, we can find the other two unknowns. So, but before that, we need to find this x because we said it's 100% excess. So we need to find this x first. How much number of moles is present? So how do we do that? So if you want to know how much is excess, first you need to know how much is right amount, right? So basically we need to find stoichiometric reaction. So in a stoichiometric reaction, what would happen? In stoichiometric reaction, we will have ideal combustion products. We do not have this additional CO and other things. The um reaction is ideal. What are the products you would expect? ATX stoichiometry. Is this clear why we are first finding the stoichiometric reaction?
Yes, sir.
No. So, if in a stoichiometric reaction, what would happen? Basically, what would happen is you will not have this additional CO, uh, OH, those atoms. Instead, you will have ideal combustion products. So, for any combustion, the ideal combustion products is you. So, in a fuel side, if you look at it, it will be a hydrocarbon. Let's say, for example, if you take a petrol, okay, nothing but a C10, I guess, C10H20 or H10, something around that. So you will have a hydrocarbon, similarly diesel also, right? So you will have a hydrocarbon. What you are doing is you are converting that into carbon dioxide and water vapor. That is the combustion process. So you are oxidizing that hydrocarbon. So when you oxidize a hydrocarbon, you will end compounds like CO2 and H2O. So for any stoichiometric reaction, what you have to do is you have to consider only the ideal combustion products. So the ideal combustion products is nothing but CO2, H2O, and since you have air here, you will have nitrogen also, and this nitrogen will not react in this ideal combustion. So if that is the case, this could be easily solved, right? So you write it A, B, and C. Now you have four atom balance and you have four unknowns. So this could be easily solved. X's A, B, and C. So you can simply do this balance equation. Let's say for carbon. So in the reactant side, how many carbons we have? We have one carbon, which should be equal to then the product side. We have A times carbon plus there is no other carbon. So basically one. And say if you have a hydrogen, let's say in the reactant side we have uh, H3 and H, right? So 4 exactly, and 4 is equal to, here you will have 2B.
Yes.
This will give B is equal to 2 if you take oxygen atom. So how many oxygen atom here we have? We have one in the fuel, we have yes in the oxidizer, and this will be equal to 2 in the carbon dioxide, 2A, and 1 in the hydrogen, sorry, water vapor. So if that is the case, we already know B and A, then we can find X's. This is going to be 2 plus
plus B minus 1 upon 2.
Right, exactly. So if that is the case, what would be excess? 3 by 2, right?
Mm.
And now we have nitrogen. So for nitrogen, what do we have? We have nitrogen is present only in the air. So basically we have 3.76 moles of nitrogen. Actually 3.76 mole into times excess, right? Is equal to 2 times C. Which is this coming out to be? C is going to be, this is nothing but 3 by 2. So C would be 3.76 into 3 by 2. Right? So if this is the case, you can write the stoichiometric reaction. Let me just write.
We can also write the value of B here.
Where?
3.7 B. 3.76 is?
3.76 is the,
Okay.
uh,
Sorry.
so for B
I thought
is,
it was B.
oh, okay, okay, okay. All right. So if that is the case, let's, so it's clear now, right?
Yes, sir.
Okay. So let me write it down here. This is going to be 3 by 2. A is 1, so you don't need to write anything. And H2O is 2, and C is nothing but 3.76 into
3 by 2.
times N2. This is basic thing, no problem. Now it's uh, so this is the stoichiometric. This is the right amount of air. Now what the question said is I have 100% excess, right? Which means twice the amount of air I have. So if that is the case, 100% excess air, how would you reframe the reaction? So it's going to be CH3OH. Now what we have is we already found this X basically.
Yes.
Basically what we are telling is this X is going to be XS times 2, and XS we already found it's going to be 3 by 2. So basically we can replace X to be 3, right? So now what do we know? We know that we also know that during combustion 60% of carbon in the fuel is converted to CO2. So which means uh, this CH3OH, we have 1 mole or 1 kilomole is actually converted into, so 60% is converted into CO2 and 40% is converted to CO, which means if I have 1 kilomole I will have zero point 0.6 kilomole of
CO2.
CO2. So basically I will write zero point 0.6 kilomole. Similarly here I will have zero point 0.4 kilomole. Now this would be useful when we have when in this reaction. So in this reaction what we could replace, we could replace uh, basically A to be zero point 0.6, right? Because since we have 1 here, we can A 6 and B to be zero point 0.4. So basically what we did is we already did carbon balance in this setup. So we used carbon atom balance in addition to whatever given in the question. Use that to find this We have three more atom balance to do with oxygen, and we have C, D, and E as unknowns. So that could be easily done, right? So that's because the system is closed. So if that is the case, let's write a hydrogen atom balance. What would happen? Hydrogen. Here it would be same 4. 4 would be equal to 3, right? So C will be equal to 2. Similarly, if I write oxygen atom balance, it would be 1 plus 2 times, which will be equal to 2A D plus C plus 2D. We have a lot of things here. So now this would be 1 plus 2 into 3 is 6. 2 into A is 1.2. B is zero point 0.4. C is 2 equal plus 2D. So this can, then you can find D easily. So what is the D it's coming out to be? It should be 7 minus 2, which is 5, minus 1.6 maybe. So probably it will be around 3.6 or 7, 7 minus 2, 5, 5 minus 1.6 is 3.4, right? It's 3.4. And finally, we have to do nitrogen balance. So what is the nitrogen balance over here? We have 3.76 times 2 into x, 3.76 times 2 into x times e. So then you can write e to be 3.76 into x is 3 into 3.
3 by 2.
X yes is 3 by 2, right? Stoichiometry was 3
Yes.
by 2. Now we have 100% XSR, so X would be 3. Okay, is that clear?
Yes.
Yes, X is 3, A is, yes, it's zero point 0.6, and CO is zero point 0.4, and C is times H2O is T, which is 3.4, and N2 is 3.76 time, times 3. This is how you will balance the equation. All right, so we wrote the balanced reaction equation. So this is done. Now we need to determine air fuel ratio. So how do we write it? How do we determine it?
Uh,
So what do we mean by air fuel ratio? So it is actually simply written as A by F. Uh, so basically, yeah. So
yes.
if that is the case, then what would how would you find it? Mass of air. What we know was we know moles of air. Let me write it down. So moles of air and fuel. What is the number of moles of air we have in this reaction? This is fuel, right? So what is the number of
Yes.
moles? Number of moles of air? Number of moles of fuel is 1, no problem. Is number of moles of air 3?
Yeah.
But air contains both O2 and N2, right? So we have 1 mole of or 1 kilomole of O2 plus 3.76 moles of N2. So basically, air contains 4.76 mole. So 1 mole plus 3.76. So it is not just 3, it should be 3 times 4.76. Is that clear, Richa?
Yes, sir.
So if the moles of air is known, then you know how to do it. It's just going to be moles of air times molecular weight of air.
Yes.
So fuel by molecular weight of fuel.
Yes.
Right? And of air is, I guess it's around 29, right? 28. And moles of fuel is 1. And molecular weight of fuel. How do we find molecular weight of fuel? Just need to add weight of individual atoms here, right? So we have carbon atom which is 12, and we have 4 H atoms which is 4, 16 plus
32.
total is 32. Thank you.
Yeah.
Right, 32. So if that is the case, how much is the air fuel ratio coming out to be?
Twelve point nine four.
Actually, it would be no unit, but it is better to write it as kg of air by kg of fuel. Okay, kg of fuel. So that's it for this problem. So we found air fuel ratio, and we also found the balanced reaction. So that is fine. So do you have any questions in this problem, Richa?
No, sir.
There are no questions. I will move forward with the second problem. So the second problem here actually deals with a, fuel rich mixture, but it says fuel rich mixtures, but we'll come to that. Fuel rich mixture of MMH and N2O4. So do you have any idea what is MMH is? So it is nothing but it's actually a propellant used in rocket called monomethyl hydrazine. It's one of the liquid propellant which is used in rocket. So the chemical formula for this is CH3NH2. Basically, it's an hydrogen, and in that it's nothing but hydrazine. In that one H is replaced by a methyl.
Group.
So N2O4 is the oxidizer here, and they are doing is the fuel rich mixture of MMH and N2O4 at a oxidizer fuel ratio of 2.0. Here we say oxidizer fuel ratio
Yes.
because air is not our oxidizer here. We have N2O4 as an oxidizer. So air fuel ratio and oxidizer fuel ratio are same. Only thing is, instead of air we use some other oxidizer. That is the reason we have oxidizer fuel ratio. And the oxidizer fuel ratio is given. This is the ratio at which it is mixed, and at initial temperature of 25 degrees Celsius is used as a liquid bipropellant rocket in a bipropellant rocket. Now determine the following they are saying. They are asking us to find the balanced reaction for this.
Yes.
What would be the balanced reaction, and the energy released during the combustion, and also adiabatic flame temperature. And finally compare your results with NASA. Okay. So first, what we do is we let's start writing by a balanced reaction. So I just draw a rocket engine actually, a liquid rocket engine. So basically, there will be a fuel supply in supply or oxidizer supply, and it will be mixed inside the combustion chamber. Actually, it will not be this straight, it will be like slanted like this, so that both the jets will meet and then it forms small droplets. And once it forms small droplets, it will get ignited, and once it ignites, the flame will propagate and then combustion happens basically. So once combustion happens, this product CO2, H2O, all these products will be formed in the combustion chamber. So now all these combustion chamber, the products are at gases. So these gases, it requires a nozzle to accelerate. Do you know what a nozzle is, Richa? It's a CD nozzle. Are you from mechanical or chemical engineering discipline?
So I'm from a chemistry background.
Oh, okay. So you are from a chemistry background. So
Yes,
you may not know what a CD nozzle is. Do you know?
yes, sir. Yeah, actually, I have an interest in thermodynamics and combustion. That's why I have joined this course, and I'm also doing PhD. So somewhat it is related with my work.
I see. So in which area you are working in PhD?
Actually, in biofuels.
Biofuel. So you mean you would use methane, is it? Methane
Yes,
combustion, is it?
yes,
Okay,
sir.
okay. All right. So actually, I'm also a PhD student. Um,
Ji.
I work in rocket propulsion. I actually work in solid propellants and its combustion behavior and its propulsion behavior. I do. So that's why this combustion course is actually the fundamental course for me. Combustion and CFT courses are fundamental. So basically, what would happen in a rocket nozzle is, so you know what a combustion is. Combustion, it will be uh, converting this internal chemical energy into a thermal energy, right? So you are converting
Yes,
it
sir.
into a thermal energy. So, but in rocket, what we are interested is in we are interested in the force. We require force to propel the rocket into the space, right? So, if you want force, you need to convert that thermal energy into a kinetic energy. That's why you see lot of gases has to be uh, pushed out with a higher velocity from the rocket. So that's why you see when you see a rocket launch, you will have a lot of gases coming out of the rocket. Right? So if you just let the gases come out without this CD nozzle, it will have very less velocity. But this CD nozzle actually acts as an accelerator. So it accelerates the gases from low speed to high speed.
Hi.
Basically, here the speed would be in subsonic, here the speed would be in supersonic. Okay, so when you increase the speed, you will get more force for a rocket. That is the reason we fit a. So what we have is we will try to generate lot of gases in the rocket, and what we try to do is we will accelerate to the nozzle. That is the main theory of the generate these gases, and to generate a very high energy gases basically. And that is the reason the combustion chamber is there, and we have a combustion happening inside this combustion chamber, and then we accelerate through the nozzle. So that's why the nozzle part is there. But basically, here in this question, actually, we are interested in what is the combustion, what are these products, because these products are going to get accelerated, right? So we need to know what are these products and what is the temperature here. basically I'm converting the thermal into a kinetic energy here, right? So that's why I need to have a very high thermal energy. That is my interest. So that is why I need to study how the combustion happens inside a rocket motor, and what is the highest temperature you can reach, and what are the products you can get at the end of this combustion chamber. That is going to ultimately affect my of a rocket. So that is the reason we actually study these things for any combustion system. And for this question, we are interested in finding the reaction so that we will know product composition and the energy. Use this energy release for this conversion. And the adiabatic flame temperature and energy release are actually related. Both represents the thermal energy of the system. So, having said that, so is that clear the problem setup?
Yes, sir.
Uh, now that the problem setup is clear, let me write down the equation. It's going to be CH3, NH, and
NH2
H2. Wonderful. We have N2O4. We don't know
and
how
2.
many. We don't know how many moles are present. So, and also we also know oxidizer fuel ratio, which is going to be 2. So based on that, you can find what is this thing you can find, right? So now my question is, what would be these products? What are the combustion products I should assume, or what are the combustion products will be there? Can you guess what would be this? What are the possible combustion products? What do you think? What are the so here we have carbon, same thing, carbon hydrocarbons you have in addition nitrogen also oxygen. What are the combustion products you would expect? Basically, everything is going to get oxidized, right?
Yes, sir.
So what would you expect?
The same CO2, CO,
We have so H2O,
yes, H2O, N2.
and then
Do we have methane also?
why not a methane should be there in the products, right? So because we have methane, once
Yes, sir.
if the bond breaks, you can have methane also.
CS4. Methane CS4.
Sorry, methane CH4. This is methyl group. Sorry. If you ask me, I would
Yes,
write
sir.
O2. Why not? I would write
Yes, sir.
O. I would write H. So write O3. Actually, ozone also forms.
Yes. Yes, sir.
H3.
Ammonia.
What else it can form? OH. OH is an important species in the product of combustion. Actually,
Hydroxyl group.
I can have hundreds of compounds like this. I can keep on
Okay.
going.
Yes, sir.
My question is, how do I find this product composition? It's a question, right? So you see, you have only uh, H, N, and O. You have four atoms. You can do atom balance and find only four unknowns. Here I have hundreds of unknowns. I can have n number of species. I can keep on adding, right? Why should
Yes,
I restrict myself to only in the last previous problem? It was written
question.
just it was given that only these are found. In fact, in
Yes, sir.
reality, it's not the case. You can add O, you can add H, you can add N, you can add N, sorts of things. But with this, the problem it gave that it is the thing. But this problem didn't say anything. I have a lot of unknowns. How do I solve it? Right?
Yes, sir.
This is so basically in any let's say studies related to transport phenomena basically uh, is actually guided by only three principles. One is mass, right? Mass conservation, momentum conservation, and energy conservation.
Yes.
Only these things are these are the fundamental laws based on which you can solve any problem in the uh, engineering. In this, at least in the transport phenomena, we have momentum conservation and we have energy conservation. Here we are not worried about the change in velocities and momentums, what are the things, so we no need to solve for momentum conservation. So here we already used mass conservation. What is the mass? We have four. This atom balance is nothing but a mass conservation, right? So we know this much amount of mass. This mass of carbon can give only this mass of you know uh, carbon dioxide, or this much amount of carbon in the carbon dioxide can will not it's not going to change from reactants to product. The mass of carbon present before and after is going to remain same. Only the form it takes will change, right?
Change.
So
Yes, sir.
so basically we used for atom balance we used basically we used mass conservation. This is actually not needed because it is not uh, useful in this present scenario. We are not interested in how it moves, right? We left is energy conservation, right? But for energy conservation, in energy conservation what we find is we find temperatures. It has for to find the temperature you need product composition. This needs product composition. If you remember, this temperature is nothing but the adiabatic uh, flame temperature, right? So to find adiabatic flame temperature, you need product composition. My question is, I used all the fundamental equations. So this is the problem I have. How do I find this product composition? Do you have any idea? Or did we miss some fundamental concepts here? Uh, what we can come up with to find the composition of products? So did we miss any fundamental law here in order to uh, so that if we use that law we will be able to get a product composition? All right, you are thinking too much. I will give you the answer. So basically, energy conservation is nothing but first law of thermodynamics, right?
Yes, sir.
What is the other thing you need to satisfy in order to say that physical system? See, you have to use second law of thermodynamics.
Entropy.
Exactly. So you need to use second law of thermodynamics. Uh, so second law of thermodynamics is nothing but delta S of universe or change in universe is always going to be negative, right?
Yes, sir.
Entropy will always maximize. So you need to use this information to get product composition. Okay. So that is how this whole system gets closed. But how do we use second law of thermodynamics for this? We have four atom balance, and one more thing is, so in order to fully define any combustion system, you need to know define combustion system, you all the composition of products. In addition to that, you need to know the adiabatic flame temperature, right?
Yes.
Friction plus adiabatic flame temperature. Only these are the things, product and reactants also, because only if we know reactants we will get the products. And adiabatic is as T adiabatic. Okay. These are the two things you require in order to get define a system, combustion system. So now if that is the case, here the temperature can be used solved using first law of thermodynamics, but and the product composition actually has to be solved using second law of thermodynamics in addition to the mass conservation. Okay, mass conservation cannot be violated. So second law of thermodynamics, we need to use second law of thermodynamics to find this product composition. Basically, how did we use second law of thermodynamics? We know second law of thermodynamics is that the entropy change of the universe is going to be greater than zero. So
Then zero.
right. So the one more. So but it is talking in terms of universe, which is system plus surroundings, right? So we know what happens in
Yes.
the surroundings. We don't know how the surroundings will behave, what are the things will happen. We don't know those things. So converting this second law of thermodynamics to a statement where you can analyze one system is, so you convert you the delta S universe is greater than zero can be actually converted into delta G, which is less than or equal to zero, right?
Yes, sir.
But gives free energy.
Free energy.
So what you will try to do is you try to minimize this Gibbs free energy for a when you try to minimize the Gibbs free energy, you will end up getting a, okay. So you need to minimize the Gibbs free. So minimizing Gibbs free energy is nothing but maximizing the entropy. So basically, in that way, you always greater than zero, and you will have maximized entropy, and universe always tends to go there. So that is the reason we use second law of thermodynamics to find the um,
Product
product
composition.
composition. Now we have to use Gibbs free energy, and for that we need to know. Uh, so basically, what happens is in any combustion, ideally CO2 and H. Ideally, you want CO2, H2O, and N2. You do not want anything else. But because of the temperature is going to be very high. With high temperature, the CO2 bonds can break. it can dissociate and become CO and O, right? So you will get CO and O, additional products. And H2O can dissociate and get H and OH. Okay, and these H's formed, this H formed can combine into two and can come up with H2, right? And the formed N O can actually react with N2, right? And form NO2 species, and the O's can combine together to form O3. So all this dissociation and recombination reaction is what giving rise to all of these products, right?
Products.
So, so yeah, CO2 and H2O, which is formed, which is oxidized, actually dissociate and undergoes and recombination reactions and try to form the all set of products. So now what we need to do is, if CO2 is going to form CO and O and H2O is going to form H and OH, I need to understand how much amount of H2O can dissociate and form H and OH, right?
H.
And that dissociation will be given by the that dissociation too should follow the second law of thermodynamics. The recombination also again should follow the second law of thermodynamics. So you will have number of Gibbs free energy equations for each and every uh, what do you call the react equilibrium reactions, right? So the combination dissociation reactions are actually equilibrium reactions. H2O can go to H and OH, H and OH can come back to H2, right? So that is the idea behind this. So what you have to do is, in addition, you need to consider, let's say, dissociation. If we consider H2O dissociation, what happens? H2O can actually dissociate. It can go either side and becomes H and OH. Okay, and now this can be understood by KPs, right? The equilibrium constants. Uh,
Constant.
so KP, you know how we can write KP. KP is going to be product coefficients. This is maybe reference and CPH by P reference. These things you must have learned. Uh, so this is how you write KP, and basically what happens is, this KP is, so if once you do Gibbs free energy minimization, you can actually come up with KP relation, where KP is nothing but exponential of minus delta G for this reaction, H2O dissociation reaction, divided by RT. Okay? G of H2O, delta G of H2O is nothing but H2O dissociation reaction. This is for a reaction. So this is nothing but G of H plus G of OH minus G of H2. Nothing but products minus reaction. Gives free energy of products minus reactants. So similarly, so this would give you, so basically KPs you can write in terms of mole fractions. Okay? So you can write x of OH plus x of H divided by x of H2O, and which is equal to exponential of minus delta G H2O G naught divided by RT. Okay, and now this will give you this is one of the equation you need to solve together. This is one more equation. So this is one equation. Let's say we call it 1. Similarly, you need to use water gas shift reaction, which is nothing but CO2 plus I think H2 is going to give CO plus H2O. And you write the Kp equation for the same thing. That will be your second.
Yes.
Similarly, you write O2 dissociation, uh, H2 dissociation maybe, and simply you keep on writing what are all the possible reactions one it can happen within the uh, combustion system, and all these will result in number of Kp equations, and these Kp equations in addition to this four atom balance, if you solve it together, you will end up. It is a little bit complex process, uh,
Yes.
but that is why in all the problems provided in, let's say, in your assignment or the first problems, they have clearly told that these are all the products and this is the mole fractions of the products. And finding all this, it's going to be very difficult and it's going intensive, but people have done it. If you take a separate combustion course, you would be asked to do it as a assignment for this. Okay.
Okay.
um, but in the interest of time, what we do is, is that clear what I'm trying to do here?
Yes, sir.
Okay. So if you couldn't understand it, please let me know. Okay.
Yes.
Basically, what I'm trying to do is I'm trying to match unknowns and the equations. Okay, so that I can and I can solve. And if you look at it, these equations are actually non-linear because it has exponential term in it, and it also there is a multiplication of mole fractions in it, right? So these equations will give you mole fractions, and based on the atom balance, you can find all the compositions here, but it is not feasible to do it by hand. That is the important problem. But you can use a computer, you can take help of a computer, you can solve it numerically
Okay.
for this kind of problem. That could by hand is going to be difficult. So what we are going to do is we will restrict ourselves with certain product species. Okay, I could have started with that assumption, but I wanted to let you know the process of finding all these things. Okay, and also we'll come back to it, what is the impact of making this assumption. Okay, so the assumption is, let's say we will have only CO2, CO, H2O, and N2. Okay, only four products, so that one atom balance would be enough to solve this kind of system. Okay,
Yes, sir.
and it also makes sense to select these four products because hydrogens are can be easily oxidized compared to carbons. So whatever hydrogen is present, oxidation can actually favor to form uh, H2Os, and carbon oxidation will take some time. So it's better if we use H2O. We could have also used H and OH also in the in addition to this, but it complicates the solution process. So basically, what we are going to assume is, we are going to assume only these are the products present. Okay, so if that is the case, it should be easier for us to solve now. So let's try to write down the balanced reaction again. So we have H2, right? In H2 is
That's into four. See.
is uh, CO2, CO, H2O, and N2.
Yes.
Now what we know is, we also know oxidizer fuel ratio, which is equal to 2, which is going to
Two.
be mass of oxidizer by mass of fuel. Mass of oxidizer we already know, N, it's equal to number of moles of oxidizer times molecular weight of oxidizer, N2O4, of fuel, which is mmH, and molecular weight of the fuel, which is mmH. So number of moles of N2O4 is what we need to find, which is X, times N2O4 is 28 plus 16 times 4, 64. 64 plus 28 is going to be, how much is that coming out to be? 8, 92. So N2O4's molecular weight is going to be 92. Okay, and we are taking this to be 1. So if it is 1, is going to be, sorry, one carbon atom and six hydrogen atoms, and which is going to be 28. Now this is going to be equal to 2. So now x is going to be x coming out to be, this 46, 92 by 46 is actually 2. So x probably will turn out to be 1,
46. Yes.
right? So we found x. Okay, x is done. Now we can just simply do atom balance to find the others. So let's say
Hmm.
in atom balance, if we do, is going to be 6 on the fuel equal to 2c,
2.
is equal to 3. Oh, sorry. Right. So it's just hydrogen, right? So hydrogen means 2c, right?
Yes.
Am I-
Yes, sir.
So c will be just 3. Next is nitrogen, let's say. If we put nitrogen, we have 2 on the fuel and 2x oxidizer, which is going to be
3. 4. 2D. D is equal to 2.
plus 1, 1 x plus 1 is 2. Okay. And oxygen, what would oxygen give? Oxygen balance would be, we have 4 times x in the oxidizer, it's going to be 2 times a in the uh, carbon and 1 times b, and then c. One more thing. So when we did carbon balance, we said a is equal to 1, but actually there are 2 carbons, right?
A
Carbon
and
dioxide and carbon monoxide is there. So actually it should be a plus b equal to 1. That is one equation, and this is going to be another equation. This can be written as 2a plus b is equal to, c is 3, x is 1, so 4 minus 3 is 1. Okay, so you have this equation, you have this second, solve it, right? So let me write it down here. A plus b is equal to, if you subtract these two equations, you will end up getting a is equal to 0.
A is equal to 0. And the B is equal to 1.
E will be 1. Wonderful. So basically what this tells is, the once we assume this, we it is actually CO2 is not at all present. Okay, so that is
Yes.
what it is telling, no CO2 present. But it is an assumption. In a real system there will always be CO2.
Yes, sir.
We write it down, CH3NH NH2. How much CO? CO is B. B is 1, so CO plus H2O is C, so 3 times H2O times N2. This is actually your balanced reaction. Okay. Um, for the oxidizer fuel ratio of 2. Now have to find what else we need to find. We need to find energy release. So this is done. We need to find energy release during combustion. So what it means, what does energy release means? So if you have gone through the lectures, this is nothing but the enthalpy of combustion. Okay,
Yes.
energy release during combustion. This is nothing but enthalpy of combustion. So we write enthalpy of combustion. What has been followed in the lectures, but please recheck once. So for now, write delta H of combustion. Okay, so that is the energy release of combustion, which is nothing but It's the enthalpy difference between products and reactants. Okay,
Reactant, yes.
you can write it as NiHi. So I use bar because it is in terms of moles, minus. So this is products minus summation of NiHi bar reactants. This can be written as N of CO, H bar of CO plus N of H2O, H bar of H2O plus N of N2, H bar of N2, right? The reactants, which is N of mmH times H bar of mmH plus N of N. We need to do what is this enthalpies? So enthalpy of any species, molar enthalpy of any species can be written as, you remember, it's going to be H HF of I. Probably it may be delta HF, something like that. It's nothing but formation enthalpy, which is at 298 Kelvin, plus the sensible enthalpy, which will be from 298 Kelvin to initial temperature, times E of dt. Okay.
Yes.
Okay. So in our case, the initial temperature is given as 25 degrees Celsius. So because of that, you can write it as 298 Kelvin. We know that T ref is 298 Kelvin. So basically, this part goes away for reactants. Okay. And also, we are trying to do is we are trying to find the enthalpy of energy release during combustion at the same temperature at 25 degrees Celsius. We are trying to find, which means I converted the reactants to products. While I convert the products, my temperature will rise, but then I cooled down to 25 degrees Celsius. When I cool down, I extract some heat, right? So what is that heat is what enthalpy of combustion is. So is that clear?
Yes, sir.
Right?
Yes, sir.
Huh. So what is the amount of energy you can extract for reactants and products when the reactants and products are in the same temperature? Let's say you start from 25 degrees Celsius and you convert all the reactants to the products, and again you come back to 25 degrees Celsius, and when you in this process you have to extract some heat, and that heat is nothing but the energy released during combustion or enthalpy of combustion. So here all these H bars you can actually replace with HFs, formation enthalpies. So basically you would expect something like H bar of CO is nothing but CO. So I have data for this. This can be taken from the tables. So delta HF naught of CO is minus 110.54 kilojoules per kilomole. Okay. And similarly, H bar of H2O, this can be written is just formation enthalpy for now. This is equal to minus 241.845 kilojoules per kilomole. And what else we have? H bar of N2. H bar of N2 is also again it's enthalpy of formation. The definition of enthalpy of formation tells is um, if it is a naturally occurring element, right? Like for N2, it naturally occurs as a gas, or any element which naturally occurs as a gas has a formation enthalpy to be zero, not as a gas at a T reference and 3 Kelvin, whatever here in its naturally occurring state has a enthalpy of formation to be zero. Okay, let's say for water, if it's a liquid water, uh, liquid water is not an separate element, it is a compound. But if you
Yes.
take oxygen gas,
Yes.
oxygen actually appears as a gas in its natural state, so its formation enthalpy is zero. But if you take
Similarly,
carbon,
here N2 is also zero.
right,
Formation enthalpy of N2.
right, exactly. Similarly, if you take carbon, carbon actually naturally occurs as a solid at 298 Kelvin and 1 atmosphere pressure. So carbon solid is has a formation enthalpy zero, but
Yes.
carbon gas or carbon liquid doesn't have formation enthalpy to be zero. So you should be careful with that. Only elements, in fact, elements which is naturally and at its naturally occurring state
Okay.
at 298
Yes.
Kelvin and 1 bar pressure is going to have formation enthalpy to be zero. That is so. In that case, H of N2 is going to have zero. And also, I also have MMH, which is going to have delta H formation of MMH. I have the data for that. It's going to be 54.14 kilojoules per kilometer. H bar of N2O4 we would have 9.63 kilojoules per kilometer. Just need to substitute in this formula to get it. So let me write it down. The H of combustion is going to be, we already know the moles which we found it using atom balance equations. So now we have N of CO. So CO is 1. So 1 times minus 110.54. 3 times H2O. 3 times minus 241.845. So how many you have? 1. So I have 1 times 54.14 plus 1 times 9.63. Which is this coming out to be? So is this clear what I'm trying to do here?
Yes, sir.
So were you able to calculate the enthalpy of combustion?
So minus 899.845.
So this is nothing but it should be in kilojoules because we already multiplied by number of moles.
Yes.
Now we have this is the enthalpy of combustion. So this is how we find enthalpy of combustion. So enthalpy of combustion is just the difference in formation enthalpies of products and reactants. That's how you will find it. Final one is adiabatic flame temperature. Third one, adiabatic flame temperature. How do we find adiabatic flame temperature? So initially we have reactants and we allow it to combust in a adiabatic, let's say, setup. Okay, then which means no heat is allowed to go out, and also no work is allowed to go out. So as per the first law of thermodynamics, what it will give is it's going to give the enthalpy of reactants equal to enthalpy of products. But doesn't mean the temperature will remain same. The reason is uh, we because of it undergoes combustion, the atoms change, right? So the reactants changes into products. but reactants and products have different energy levels. So those energy levels actually give rise to increase in temperature. Even though enthalpies are same, temperatures will rise. So that is where the definition of enthalpy comes into picture. So here we write so if you just write enthalpy is nothing but CPT, you would tell that the temperature of reactants and products should remain same, right? But not CPT. The reason is already saw in the last section, we write
Yes.
enthalpy is a addition of formation enthalpy and the sensible enthalpy. So in addition to CPT, there is additional term formation enthalpy. So till now in this thermodynamics course, you would have just wrote H is equal to CPT, but in combustion you should not do that. Okay. So this is nothing but so H of any reactants is nothing but Ni times Hi bar, which is nothing but Ni times delta H naught F of which is a formation plus integral of from the reference temperature to that temperature, okay, times Cp, which is also in molar basis, times dt. This is how you write enthalpy for any species, okay, any product species or any reactant species. So having said that, let's try to find the enthalpy of reactants. It's going to be N of mmH H naught F of mmH, formation enthalpy of mmH, plus integral of T ref to T initial temperature, because we start the combustion at some initial temperature, times Cp of mmH times Tt, plus N of N2O4, this is an oxidizer, and delta H naught F of N2O4 plus integral Cp Dt, T ref to T initial. We already noted that T ref is starting at T ref, which is T initial. So basically I can remove these two terms. T ref is equal to T initial. This term also goes. So there won't be any sensible enthalpy part in our enthalpy of reactants. So if that is the case, then it's going to be simply N times mmH delta H naught F mmH plus N times N2O4 H naught F of N2O4. I think it's 54.14 and 1 times 9.63. Yes. So this is going to give, how much is this going to give? Is this coming out to be 63.77?
Yes, sir.
Alright. So this is the
60.
this is the enthalpy of reactants. So enthalpy of reactants is 63.77 kilojoules. Now let's write the enthalpy of products. But the products will be at adiabatic flame temperature. Since we put it in the, it is going to be a function of adiabatic flame temperature. Since it's in the adiabatic vessel or an adiabatic setup, uh, there is no heat loss, so temperature is going to rise. That is the case. How do we write it? Enthalpy of products, we can write it as N of CO times HF naught of CO plus P per dt time T ref to T adiabatic. T ref, let's write T ref as 8 simplicity plus N times H2O H naught F of H2O plus integral of 298 times T adiabatic dp bar of dt n times what was the other one, n2, right? Cp bar dt. Now, actually, we need to have a Cp to be a function of temperature because we are in Cp should be a function of temperature. Cp will be a function of temperature, but the function of temperature, solving it by hand is going to be difficult. We are using computer, we can use it. So for this case, assume that Cp is not a function of temperature. And I have certain values from the table. P bar of Q is going to be 37 kilojoules per kilomole. P bar of H2O is going to be 58 kilojoules per kilomole. P bar of N2 is going to be around 37 kilojoules. So then there will be only one unknown, which is T adiabatic, and if you equate this, let's try to find out enthalpy of products now. Enthalpy of products is going to be N of CO is 1 times HF is minus 110.54 kilojoules. T is 37 times uh, T adiabatic minus 298 plus H2O. H2O has 3 moles of H2O minus, I think it's 241 point, how much is that? 5? 37, not 37, 58 adiabatic minus 298 plus N2. N2 is, I think, 2, right? 2 moles of times 37 times T adiabatic minus 298. Add all the CPs together and all the enthalpy of formations together. If we do that, 110.54 3 times 241.845 will give you minus 836.075 kilojoules, plus I have 37 times T adiabatic minus 298, and I have 58 times 3, plus I have 2 times 37, all gave me 285 times T adiabatic minus 298. Okay. And we know that H reactants is equal to H products. We already found H reactants. H products. H reactants is also 67, right? Something we found. 63.7. So here it is. 63.77 is equal to minus 836.075 plus 285 times T adiabatic minus 298. Okay, so let's say if you take what would be the T adiabatic? This can be easily solved. 36.075 so these are in kilojoules, so make sure you and multiply it properly. 10 power 3 and 10 power 3. Are you getting? So is it around 3455 kelvins?
Yes, sir.
So this is the T adiabatic temperature, and this is how you find it. It's around 3000. So mostly adiabatic flame temperatures will be around 2000 to 1000. Actually, here we consider only a small amount of products, and we didn't consider dissociation, we didn't consider recombination. These are endothermic process. So it actually you will get lesser temperature than this. But let's say if you want to find the realize more realistic value, okay. So let's say if I want to find what is the more realistic value of more realistic value of T adiabatic. For that you need to solve those KP equations. You see the equilibrium. Basically, you need to Gibbs free energy, minimize Gibbs free energy, and find all the product composition. And actually you will end up getting system of equations, which system of coupled equations, so lot of Gibbs free energy equation in addition to the energy conservation equation, the H reactor is on the whole in a, let's say in an iterative process or something, you will end up getting a value of adiabatic flame temperature. But uh, find all the product composition, but doing this by hand is possible. So that's why we use certain softwares like we use NASA CEA. So have you heard about NASA CEA, Richa?
No, sir.
NASA CEA, and we have Cantera, we have other softwares like this. So this NASA CEA and Cantera are open source. It is easy. It is not licensed. Anyone can use it, and it is available online also. So what I will do is I will try to show you how to do this adiabatic flame temperature calculation. See, would you be interested to know that?
Yes, sir. Sir, I have one request. Sir,
Uh-huh.
will you please provide the answers of the assignment? Because I also wrote this in the feedback form. Please
Okay.
provide answers to the maybe a solution to the assignment problems, because we have some problems during solving the questions. And how do we know that our method is right or wrong?
So, based on the questions which has been asked in the assignment, those are actually similar like what I solve and what professor solves in the class. So, um, if you the reason they are not providing solutions, you are interested to know something specific about, let's say, some problems which you are not getting answer, if you are not understanding, you can ask me
Okay,
in
sir.
this session. I would be happy to solve in front of you. That
Okay,
is
sir.
possible. But you have written a feedback form, right, to provide solutions. So they might take some, won't be a problem.
Okay, sir. Thank you.
So what we try to do is we'll try to solve the same thing, but with NASA CE. Okay. You can do, actually you can do for any systems. You can do, let's say for example, yours like methane, for biofuels, methane combustions you can do. um, what I would do is I would send it from my computer. My screen visible, Richard?
Yes, sir.
So if you search for NASA CEA, okay, so nothing but chemical equilibrium analysis. Um, CEA means chemical equilibrium analysis. So what we do is what we are trying to do is we are actually finding equilibrium between these two, between dissociations and recombinations, right? So that is why it is like this. So if you search in Google, the first link itself, you will end up getting. This would be the interface uh, for the CE analysis, and here if you look, you will be asked to select the problem and code, right? Chemical equilibrium problem. There are different problem types. All these are, a little bit advanced combustion concepts. But our interest is this assigned enthalpy and pressure. So for a given pressure and given enthalpy, we are trying to find the equilibrium, right? So that is, select this second option, assigned enthalpy and pressure, and you can give some number. It's not required, and if you submit it, first thing it will ask you is the pressure value. So at what pressure you are trying to solve. So we are solving atmosphere, right? So
Yes.
you can give 1 atmosphere here, and this here if you look at it, there is a uh, unit for pressure, ATM. So 1 atmosphere, or let's say 1 bar also, and continue, and it will take you to a next page called fuels. So you need to select a fuel. So for example, they gave some default fuels. So one default fuel is methane. They gave methane as a liquid. L stands for liquid. They also gave hydrogens. They also gave RP1 is actually rocket propellant one. So for this case, we have to use MMH, right? Monomethyl hydrogen. So let's use, you can use periodic table also to select which one. Let's say you select the use periodic table and go. You will see a periodic table here. Here what you do, our MMH contains oxygen, carbon, and nitrogen.
Yes, sir.
Okay. These are the three things. You select these things and select accept element sections and continue. Okay. Here you will have certain fuels. So if you look at it, this fuel CH6N2, right? It will be in liquid form, monomethyl hydrogen. So this is what we are trying to solve, right, in this question. So let's say if you select this CH6 and then accept selected reactants and continue. Um, it is asking whether you want to add more reactants or not, but it is fine. I want only these reactants. If I continue it will ask me for proportion. So let's say if you have number of reactants, let's say in any fuel, you will have mixture of fuels, right? So in a gasoline, you will not only have the uh, uh, what do you call? I think it's hexane or decane, I guess. Again, in addition to certain amounts of methane and propane, all these things would be mixed, right? So if that is the case, then you have to give what is the proportion of each and every fuel present. So in our case, only we have only one fuel MMH. So let's give it 100% and we'll continue. And here we have to give temperature. The temperature is 298 Kelvin, right?
Yes.
Oxidizer. So what is the oxidizer you want to select? So default there are certain oxidizers like air, chlorine, fluorine, and side, N2H4. This is N2O4, right? So again we use periodic table. So select this option and you go select from start, 1 bar, C and N, 298 Kelvin, right? Yeah, oxidizer. And here oxidizer is N2O4, N2, N and O, and continue. Use certain things. Here you have N2O4 liquid. Let's select that and again same thing. Again, say oxidizer also can be a mixture. So right now we have the initial temperature is 298 Kelvin. Other things you don't need to. Here, finally to last, what is the oxidizer fuel ratio? In our case, the oxidizer fuel ratio is nothing but 2. So we can type here as 2, the first one. In fact, you can type here 4, you can type like this, you can keep on typing and you can see which one gives you the highest temperature. Those things you can do. You can play around with this. Say if you continue after giving, what are the parameters you have selected. So I have selected pressure to be 1 bar and oxidizer fuel ratio to be 2. Now it will either show me mass fraction or mole fractions. You can select either of it and it will show you you can select, you can perform this CE analysis. So you can basically whatever we did, this problem it can be solved via this also. So let's say if you submit input and perform CE analysis, you will end up getting results. It will show you a results page here. So if here if CE analysis performed and all it will those things, problem type, and here you will measure 1 bar. Is it visible or should I zoom it in?
Yes. Yes.
Pressure here is 1 bar, oxidizer fuel ratio is 2. Um, fuel here, as I said, it's going to be MMH and N2O4. Now it shows thermal equilibrium combustion properties at assigned pressures. So there's a fuel ratio of 3. In that fuel percentage is 33. These things it automatically calculates. It even calculates equivalence ratio, which is 1.248. In this problem, we didn't calculate it, but this can calculate and gives you thermodynamic properties here. So it gives you pressure, temperature. So this temperature is what the adiabatic flame temperature. So what we got is 3400, right? 3400 Kelvin. But the the more realistic value is actually considering the temperature dependent of CP, considering lot of x, you will have 29 I mean 2930 Kelvin as your adiabatic flame temperature. In addition, they also give rho, enthalpy, internal energy, gives free energy, all these things they will give. Entropy also. Um, Another important thing is you will have product composition here. Here you see you have CO, you have CO2, you have H, HO2, H2, H2O, NO, NO2, O, OH, O2. O H, O 2 O H O 2. In fact, there are few more. Uh, 2 O H O 2 In fact, there are few more. Uh, 2 O H O 2 O H O 2 O H O 2 O H O 2 O H O 2 O H O 2 O H O 2 O H O 2 O H O 2 O H O 2 O H O 2 few more species also they must have they would have considered, but those mole fractions would be very less. So that is why it is not coming over here. But they have considered most of these species here. So then you have, and I mean they also consider this decompositions and recombination. That is how you get CO2. We actually got CO2 moles to be zero, right? Which means mole fraction should be zero. But what happened? The O actually reacted with CO and gave rise to some CO2. Okay, and similarly H2O reacted with O2 to give HO2, and also H2 actually decomposed to get H, and H and O actually combine to get OH, and so O2s, everything is present. So all these things could happen in a real combustion chamber, real combustion system, and considering all these is essential to get a more realistic value. So we are almost off of around 500 kelvins. That is huge, right? Here we have 30 kelvins. Okay. So is that clear what I'm trying to say, Richard? All right.
This is very helpful.
Okay. So similarly, you can run for, let's say, your methane case. You can run the same thing. You can get the adiabatic flame temperatures. You no need to actually do all these calculations by yourself to find the adiabatic flame temperature. Adiabatic flame temperature is, let's say if you take a gas turbine, okay, in a gas turbine, uh, the combustion chamber, it actually enters the turbine, and the turbine is exposed to a high temperature gas. What happens is at that temperature, let's say at 2900 kelvin, a huge thermal load on the turbine. So these turbine blades can melt, or turbine blades will starts to deform. So if it deforms, it's fatal for any, let's say, engines, right? In an aircraft engine or a jet engine, it's a fatal. So that's why we need to know what is the highest maximum temperature that a turbine inlet will have. So the blades should be able to uh, uh, take only blades will be able to take only certain amount of thermal load. It will be uh, fine only if at a maximum temperature of 1600 Kelvin. So at that time, if you send a gas of 2900 Kelvin, it starts melting. So that should be avoided. So for all these engineering analysis, we require this adiabatic flame temperature of analysis. So that's why people do this CEA analysis at first. But this will give you a certain idea only, 2900 Kelvin. In reality, it will be less. So based on the instabilities, it can go above this also. That is also possible. So there will be a certain limit, let's say 100 kelvins, and people try to design their turbine for that temperature. Or based on that temperature, they will try to adjust the combustor. Okay, change the equivalence ratio. So let's say, for example, go back, oxidizer fuel ratio. I used 2, right? Let's say if I use 4, doing it. So I will have a different temperature. See 2700. Before I had 2900. Now I have 2700 Kelvin. So you can modulate these numbers, and you can end up getting good values, and also uh, say it is helpful in terms of design, and also in terms of economy when you have a gas turbine engine, because you cannot keep on spending amount in fuel. If you spend amount in fuel, prices will rise, right? So this is for oxidizer ratio 2, and if you scroll down oxidizer ratio 4, you have 2700, and if you keep scrolling down for oxidizer ratio 6, you have 2500. See, temperature has reduced. And also similarly, there has been new compounds which has been introduced, NO2, N2s, and all become high. So this NO2s are actually responsible for global warming. So you need to have less amount of NO2s or NOx emissions. So if you look at it, this is better compared to the older one. In fact, here there is no NO2, right? But NO is there. So in a way, environmentally, there's a fuel ratio of 2 would be better, but it would be fatal for a turbine. You cannot use it. So people used to find sweet spot between these two, and they try to come up with that. So even people use methane also. Recently, they have used this in so they uh, use this as a tool to find the emission what you call norms are being uh, the reason uh, you can even do similar analysis in you know uh, some more softwares also. There are a lot of softwares where you can get such where you can do such kind of analysis. um, that's it. So let me write it down that also the CA was giving around 2900 K. Yeah. All right. Do you have any questions, Richard? Is that clear? What I tried to.
Yes.
So, if you have any questions, what we'll see
So
in the
next time I
next
will
session.
ready with my questions.
Sure, sure, no problem. You can come up with your questions with, let's say, assignment problems. I cannot discuss this week's assignment problem, but I can discuss the assignment
Yes, sir.
as whose results have
The
been published.
previous. Yes, sir.
So you can come up with those, and you can solve in front of you, or you can share me how you solved, and maybe I can give you comments on it.
Okay, sir.
And you don't necessarily need to call me sir, you can just call me Ganesh. So if I may, which institute you are doing your PhD?
I'm doing my PhD from Nagpur University, and my lab is in LIT, Lakshmi Narayana Institute of Technology, which is now a university.
All right, Licha,
Yes,
thanks
sir.
for attending.
Thank you.
We'll see you in the next class.
Yes, definitely. Thank you.